Hey everyone, and welcome back to The Explainer. Today, we're going to embark on a pretty fascinating journey to deconstruct a completely hidden digital megastructure. Most of the time, we really only interact with the penthouse suites of the software world, right? The shiny apps, the super friendly user interfaces. But today we're taking the elevator all the way down into the deepest, most intimidating layers of programming reality that silently run our modern world.
Okay, let's dive straight into this. When you first start learning to code with something like Python or JavaScript, the environment is bright, it's welcoming, and honestly, it's built to help you succeed. But as we move past that sunny surface level, things start to shift. We're descending into the cold, industrial depths of software engineering. It's a harsh environment where the training wheels just completely come off, and frankly, it's where most people just turn back.
Section 1. The economics of difficulty.
So we've got to acknowledge a pretty stark reality in the tech space. The harder a programming language is to master, well, the fewer human beings can actually pull it off. And what this brilliantly illustrates is that classic supply and demand curve in action. As you move toward extreme programming specialization, average salaries don't just gently go up, they literally launch into the stratosphere. Our whole world runs on software, sure, but it heavily rewards those who can speak its most difficult, obscure dialects.
To really put that global demand into perspective, I want you to picture every single software engineer on the planet right now. Got it? Okay, now zoom way in on just that tiny sliver highlighted in blue. That minuscule fraction? They are single-handedly responsible for maintaining our absolute deepest infrastructure. We're talking intercontinental stock exchanges, operating system kernels, military satellites, and rocket systems. This massive global infrastructure rests entirely on the shoulders of this incredibly small group of people.
Section 2. C++, the industrial machine.
Stepping into C++, man, it's like walking onto the floor of a volatile, heavy-duty factory where you have complete, terrifying control. See that manual memory allocation there? That int pointer equals new int? That means you are physically wiring the memory blocks together yourself. Make even a slight mistake, and the whole system just crashes with undefined behavior. It's an environment totally obsessed with nanoseconds, which is exactly why AAA game studios rendering massive 3D worlds and high-frequency trading firms pay out millions for flawless optimization at this level.
Section 3. Rust, the AI guardian.
Now, as you can imagine, that kind of manual control comes with absolutely catastrophic risks. Because brilliant engineers kept making disastrous memory errors in C++, the industry had to build something else, a sterile, ultra-futuristic laboratory. That's Rust. So the crucial point here is the contrast. Unlike the volatile manual control we just talked about, Rust introduces a strict ownership system. It acts like a ruthless guardian, prioritizing memory safety and stopping disasters cold before the code is even allowed to run.
Just try to do something even slightly ambiguous, like, say, having two variables claim ownership of the exact same piece of data, and boom, Rust absolutely floods you with compiler errors. It's literally like klaxons going off in a submarine. Rust explicitly refuses to trust you. And ironically, because the language refuses to trust the programmer, major tech giants perfectly trust the language. They are scrambling right now to hire increasingly rare Rust engineers to replace their aging, vulnerable systems.
Section 4. Assembly, the raw machine.
All right, take a deep breath because we are plunging way deeper now. We're dropping past all the safety nets of those compilers straight into the brutal, mechanical reality of the computer itself. Down here, there is no text, none. It's just raw electricity flowing through silicon pathways. We're dealing directly with CPU registers, operating on exact clock cycles, and physically manipulating hardware with nothing but binary pulses.
Look at commands like MOVAX5. That right there is the foundational heartbeat of the machine. This is the absolute Wild West of reverse engineering, exploit development, and malware analysis. Every abstraction we've talked about so far, Python, C++, Rust, is ultimately just a layer designed to hide this exact machine from you. But the elite engineers operating at this level, they see the matrix bare.
Section 5. Haskell, the mathematical layer.
Okay, brace yourselves. We're doing a hard pivot from raw physical hardware into a totally mind-bending abstract reality. Now, what's really interesting here are concepts like immutability, monads, lazy evaluation. These often cause developers to just fall right out of the environment in sheer confusion. Programming down here feels way less like typing instructions and more like, well, proving complex theorems.
Haskell's beautiful, though, because it forces us to realize that pure fractal mathematics was always lurking right underneath our software from the very beginning.
Section 6. CUDA and AI infrastructure.
So we've looked at the micro level, right? Now we need to completely blow up the scale. We're talking colossal megastructures of massive GPU farms. Billions. Literally billions. Just let that number sink in for a second. Right at this very moment, billions of matrix multiplications and parallel computations are firing off simultaneously inside neural networks, growing across global server clusters just to train modern AI.
And all of this mind-boggling power, it's controlled by GPU kernels. These are highly specialized programs designed to execute across thousands of threads at the exact same millisecond. The individuals who can actually write these kernels and master this level of extreme parallel processing, they are the silent architects actively building the AI revolution as we speak. That's why NVIDIA engineers are treated practically like gods in today's tech landscape.
Section 7. The elite engineer.
So, what exactly happens when you combine the terrifying memory wiring of C++, the uncompromising strictness of Rust, the raw machine code of assembly, the pure math of Haskell, and the massive computing clusters of CUDA? Well, you arrive at the ultimate engineering reality. The absolute highest-paid programmers out there aren't just typing syntax. No way. They are highly compensated precisely because they willingly navigate the staggering digital complexity that the rest of humanity actively runs away from.
And honestly, we rely entirely on that exact willingness. Everything from the intercontinental internet cables crisscrossing the ocean floor to massive global server cities to high-frequency stock exchanges, all the way to bleeding-edge quantum computing labs. Our entire modern reality is powered silently and constantly by their invisible code.
Which leaves us with this final lingering thought. The deeper you understand the machine, the fewer people can follow you. You gain the power to literally move the world, but it is an inherently solitary mastery. Thank you so much for taking this descent with me today on The Explainer. But before we go, it does leave us with a pretty massive question to ponder, doesn't it? As artificial intelligence begins to write its own code, will these deep, invisible layers remain the domain of elite human engineers, or are we simply building the foundation for machines to finally architect themselves? Something to think about. See you next time.